All right. So remember, we'll just recap what we did on SARSA, learning action values using temporal difference method. So the update formula was QSTAT to be updated by QSTAT plus alpha times the new reward plus gamma times the estimate for the next steps and action pair minus the current one, right? So basically the picture was something like this, where you need all of these things. So the current estimate and the estimate of the current state action pair and the estimate of the next state action pair to be able to update this portion as well as the next reward. So once you are here, then only you can update the previous states um, state action estimate. And this was on policy. We discussed this because we are actually following a policy, and along that we are actually updating the estimates. And when we basically, what is the policy we are following? That depends on the estimates at this point of time, but then we would like to encourage exploration a bit, so we can incorporate an epsilon greedy approach at any point of time, right? So essentially at any point of time you choose the next action, you can do some epsilon greedy approach, and then you can update the previous state action pairs estimate, so that next time if you encounter similar the same state action pair ever, you will act with a better learned value. So this was SARSA, and the SARSA stood for state action reward state action. So what we will just quickly do today is just a glimpse of what we call Q learning. And Q learning is essentially SARSA slightly modified to make it off policy. So this is SARSA, right? So the SARSA thing is you follow some policy and this is your trajectory and you can update. In Q learning, what happens is, well, suppose you come to state ST, okay, and you have the estimate for QSTAT, but of course, right now you cannot update anything. Next, you again follow the next action AT, get reward RT plus 1, and you reach state ST plus 1. Now, in SARSA, at this point of time, you would go, oh, at this point of time in SARSA, what you would do is you will also select the next action based on your current policy and update QSTAT based on these SAR, SA, all these combinations. In Q learning, what we will do rather is we will look at all possible actions from here. Not 3, there may be many more. So all possible actions from state ST plus 1. And they will, these action pairs, right? ST plus 1, A, ST plus 1, A prime, all these, they have some estimates. I mean, if it's at the very initial stage, then the initialization is the estimate. If it is somewhere in between, then we have updated some estimates by then. So these state action pairs do have some estimates. And what we would do is we will take the maximum of that. Okay, so in this this round curve is essentially, I mean, we haven't really done that much in these lectures, but the backup diagram, this is just a convention to draw that we take an aggregated view of this and take a max. So we'll take a max of these as state action values, and we'll update the previous state action according to the maximum estimate of possible next actions. So what we will do is instead of updating gamma times Q ST plus 1 AT plus 1, which would have been the next action, right? So Q ST plus 1 AT plus 1, what we're going to do, we'll just explore all possible actions here, okay, and take the maximum estimate and update the previous state action pair by that. And however, although
the maximum is over QST plus 1 comma minus QSTAT, or only on
just this.
okay.
So just this maximum over just this quantity, okay. And uh, and we update this, which is the state we have visited previously in the previous step. But then we follow one of them. So we follow one of them according to the behavior policy. So we follow one of them. We call that at plus one, and then we reach another state. Again, we explore and so on. So one subtle thing here is the action we choose here may not be the max action for which this maximum comes. Okay, so the action we choose here may be something based on our behavior policy, but what we update here is based on this maximum. Now, what is the uh, rationale behind that? What is essentially this QSTAT? QSTAT is, if I am at ST and I am taking action AT, how good, in what kind of a position am I in? What could be the reward that I may get eventually, right? So that's what the value, that's what is the value for STAT, and that's what we call QSTAT. Now, what we are trying to do, instead of trying to uh, learn the value for this state action pair according to our current policy, what we are trying to do is, let us follow some current policy, but we want to learn what is the best possible value of this state action pair. Or rather, we want to learn the optimal, uh, basically we want to learn the Bellman equation, learn based on the Bellman equation of optimality. So that's what we are doing here. Doesn't matter what action I'm taking right now, the potential for this state action pair is actually maximum, is can be influenced by the maximum that you could do right now. So it may be that I'm intentionally taking some not so optimal action right now, but well, you see, you could actually do better. So suppose this is the optimal action for just this step. Okay, so maybe this is the maximum QSTA. This is the maximum, suppose, but I'm taking this action, but I will update this value according to this value. Okay. So in other words, what happens is, and so keep doing this. So in other words, what happens is that I follow some policy, but I try to learn the optimal policy, or I try to learn the values for the optimal policy. Now there is this problem of, or confusion of, uh, doing something and trying to learn something, which is essentially the main thing behind of policy. And we'll see one example also to illustrate when something about this is good and something about this is not so good. So let's look at the pseudocode again. So this is the off policy TD control. The only difference from SARSA is this portion. Okay, is this portion where we have this. So this is based on our behavior policy. This is based on our behavior policy, choosing the actions based on our behavior policy. But we are actually trying to learn Q star. Okay, so that's what we're doing. Now, so this converges towards optimality much faster than uh, on policy, provided values for all state action pairs continue to be updated. So all you have to do is, you have to, in your behavior policy, you have to keep the scope for exploration enough so that you learn all the QSSA, right? So all state action pairs values you learn, and then this converges towards optimality faster than what would have been the other way to do it. You learn, basically you learn, you switch between improvement, policy improvement, and policy evaluation, right? So rather than that, this is actually much faster. So we need to discuss what are the good and bad things about Q learning. So Q learning, first of all, one good thing is it directly tries to learn the optimal policy. And SARSA would learn a near optimal policy by exploring if you have an epsilon greedy inbuilt into it. So that is actually essential, right? So some exploring is essential, otherwise you won't be able to converge. And if we want to learn the optimal policy using SARSA, what you need to do, and that's actually true for any epsilon greedy approach, if you want to do it that way, that you need to use decaying epsilon so that initially you explore more and later on you don't explore so much, because otherwise it will never kind of converge. It will you will always follow some suboptimal policy. Uh, then Q learning, the one small problem is because it is off policy, it has a higher per sample variance. Um, and then this example is something which we should look at, which will tell you another problem with Q learning. So this example is of cliff walking. Suppose this is actually a cliff. Okay, so it's more like this side is a cliff. You may fall. The other sides are basically, they are high grounds. So that's safe. So what you need to do is you want to go from start to end, and each step is like a time taken or energy lost or whatever. So each step, so the number of steps taken is the negative of the reward. So essentially reward is -1 for all steps, but in case you fall off the cliff like this, okay, then the reward is high negative, or rather the penalty is high. So, and then you need to start afresh as well if you fall off. So what essentially happens is, if you from here, if you take the right step towards right side from here, okay, not right side, you can as well come from here and jump straight off the cliff. But from here, if you basically fall, then you have to go to start and you also get a -100 reward. Okay, so this is the model. Now, what happens with Q learning is, Q learning will learn the values for the optimal policy very quickly. And the optimal policy is this route, right? So this route is the optimal policy. And Q learning will actually learn that this is the optimal policy, that it will do very quickly. But occasionally, what can happen is that it may fall off the cliff, because you will in practice, when you actually follow, you will do epsilon greedy, so you may fall off the cliff. And SARSA, on the other hand, learns the policy it follows, so it will try not to go to the edge much, and it may actually learn a safer policy. In fact, an experiment, this is taken from Sutton's book again, for this particular, exactly this particular setting. This is just a setting to illustrate uh, one of the important scenarios of many real life problems. That this is number of episodes, and this is sum of rewards during episode. So Q learning, what happens, as you see, there is a lot. I mean, basically -50. Okay, so -50 is kind of incorporated because it actually falls off much more often than SARSA. SARSA basically probably doesn't fall off much. It probably takes this route. Very rarely it would fall. Okay, so this is the thing. So let's go back to the discussion. So that means SARSA is more conservative. Exploratory moves may have penalties, and SARSA would avoid a dangerous optimal path. And Q learning would not bother. So how do we use this? So in real life, in case you are training a robot in simulation mode, or some low cost thing, it's okay to meet an accident. Doesn't matter, it's not really costly, but you want to learn the optimal thing fast, right? So then you would go for Q learning. So when it's okay to make mistakes. However, in some other cases, it may be possible that mistakes can be costly, right? So an accident or the whole device that you are making, if it gets destroyed, then it's a lot of a problem, and so on. So then you would actually go more conservative, and you might use SARSA. Now, so that's pretty much all. Which is just a glimpse of Q learning. We would basically, I would end the syllabus. So there is something called expected SARSA, which is another slight modification to SARSA, and I mean, it has been shown to perform better than, it's more expensive computationally, but shown to perform better than QLearning and SARSA in certain cases. And then obviously there is a vast amount of literature after this. But yeah, I think as just a kickstart introduction to RL, this much is fine. Having known QLearning, one may also start to get into deep QLearning and deep Q networks and stuff like that. And yeah, so, and then obviously one chapter or one aspect altogether that we did not touch is function approximation, uh, mm, which is obviously very important, but yeah, we'll leave it out for this course as of now. Okay, so yeah, any question at this point?
Sir, here, how we are going to select the next action for the state t plus 1? Like we are in the
For
state.
QLearning?
Yes, yes.
Yeah, so that we can select the state based on whatever policy we are following. Okay. Okay.
And that policy is going to update after the episode.
The policy is going to be updated. Oh, sorry. What happened here? Yeah, so the policy is going to be updated after, I mean, not only after the episode, basically the policy will get updated according to, okay, so let's say your policy is some epsilon greedy policy. So what is the epsilon greedy policy? You have your QSTs, right? So you have your QSTs. Epsilon greedy would, given you are at any, okay, let me actually go back to this slide, so that will be better. Okay, so what will epsilon greedy policy do? Epsilon greedy policy, given you are here, it will look at all possible STATs, right? All possible STATs, and it will take the greedy action 1 minus epsilon with probability 1 minus epsilon, and it will take random action with probability epsilon, right? So basically your policy is epsilon greedy, but based on the estimates. Okay. So what you are doing here is essentially you are still following the same policy, but your estimates for previous state action pairs are changing. So right now it's not affecting your policy. Right now you are following the same kind of policy. Maybe it is greedy, maybe it is random, right? So you may be exploring or may not be exploring, but you are changing your previous estimate based on the max here. Whereas what will SARSA do? So suppose SARSA is taking a non-greedy action at this point. So SARSA, suppose this action is non-greedy. So suppose this is a random action. So the max was somewhere else, but I'm just exploring. SARSA would update based on this explored action. SARSA would update this quantity based on the explored action. Whereas QLearning will update this previous quantity based on the best possible action at this point. So
Yeah,
if you're not, sorry.
Okay, sir, I got
yeah, right. So if you're not exploring at all, then both are okay. Both are the same, right? Because if you are just being greedy all the time, then both are same. But that's something which you will never do, because then all the sample based techniques will actually not work.
Sir,
Okay?
QLearning will update this for the optimal policy which we are trying to learn, not the policy it is following, right? Like
Right.
behavioral
So
policy.
QLearning is not updating the okay. So there is a bit of subtlety in why QLearning is off policy. So there are two things here. When we discussed off policy for policy evaluation, we had to multiply with the important sampling factor, right?
Yes, sir.
We don't have to do it here. Why? When we wanted to estimate the values for just states, then all that it means is I'm at this state. What is the estimate of the value here? That means from here, what can I do? Now, from here, what can I do? That depends highly on the policy. And the policy is basically the probabilities of actions that I may take. So if you're following one policy, but you want to estimate the value for another policy, then you have to do this multiplication or basically factor by importance sampling. However, here you are not estimating values of the states, you are estimating values of state action pairs. So you are already deciding that I'm going to take this action. So the different distributions of the policy, that change is taken out of the question. So that is one reason why we don't actually need to multiply using that factor. But then your question is it learning the optimal policy? So what is it doing is it is at every point, it is updating the state values based on the greedy method. But it is not necessarily following that method. It is actually following some other policy, which may be almost greedy, which may be epsilon greedy, which may be something else altogether. So it doesn't really matter what that policy is. But at every step, it is updating the updating this according to the Bellman optimality equation. If you just look back into that equation basically. So that's why what happens is, so it's like it's just like when we looked at how we can iteratively update and converge to an estimate. So we are actually iteratively updating and converging to the estimates of Qs for the optimal policy. If we know for the optimal policy all the Q values, so Q star STAT for all state action pairs, then at any point of time we can decide to completely switch to optimal policy. Right? So behavior also we can set to that.
Okay.
Right. So that is basically what we are doing. So in other words, if you want to put it in more real life scenario, I am at any point of time, I'm intentionally exploring, but I'm also keeping track of what could have been the best thing to do. And I iteratively learn that.
Okay.
Okay, all right. So I think then let's move to. Okay, so let me actually stop the recording and start a new one.